In this section, we are going to talk about maxima and minima of functions. So here in this chapter, we're going to look at using the derivative to apply it to different situations. For this first one, given a function f of x that is differentiable, meaning we can find the derivative for it, a couple of terms that we're going to talk about here. So f prime being greater than 0 means that f is increasing. So if I can find the derivative at a particular value, and that value comes out to be positive, then I know the function is increasing at that point. Likewise, if f prime is less than 0, this means that our function is decreasing. Okay. A critical point of f is one in which f prime of x is equal to 0 or f prime of x is undefined. So this means that if my derivative is 0, then I have a critical point, or if I have a place where the derivative is undefined, so places where the limit doesn't exist, then I also have critical points. A critical point is just like what it sounds like. If I am looking at a function, it's a point that has something happening that's kind of out of the norm. Okay? If f prime of x naught is equal to 0, and the sign of f prime changes at x naught, then x naught comma f of x naught, that point, is an extreme value of f. Okay? So here, if I have a critical point where the derivative is 0, and the function changes from increasing to decreasing, or from decreasing to increasing, then I have what we call an extreme value. Okay? And an extreme value is just either what we call a relative maximum or a relative minimum. So points at where the function is high or points where it's a low. Okay? X naught comma f of x naught is a relative max if my f prime changes from positive to negative. And so here what we're looking at is if I'm looking on a graph, and this is my point x naught, if it's going from increasing to decreasing, then I can say this point here is a relative max. Okay? And likewise, if I'm looking at this one, x naught comma f of x naught, it's a relative min if f prime changes from negative to positive at x naught. And so here, same idea. I have my point x naught, but then I have it's decreasing and then increasing. So this point is a relative min. Okay. So let's look at this graph for an example. Okay, here's a graph of the f of x, and it has some various pieces of information. So if we kind of look back at what we were talking about, we can look at where f is increasing. So here we're looking at all the places where the derivative is positive. Again, derivative being positive means my slope for that part of the graph is positive. And so if I look here, I can see, well, if I think of a tangent line in this case, this is going to be a negative slope. And over here, I can see the slope is more positive. So here, starting at negative 2, up to negative 1, I can see that my slope is increasing. Okay? Also, here from negative 1, I can see from negative 1 to 0, my slope is increasing. Okay? So anytime my slope is going kind of in a positive slant, I know it's going to be an increasing function. So from 0, I can see, yeah, this isn't quite positive, but then here at positive 2, again, I'm back to an increasing slope. Okay. And then I've got kind of this weird point where it kind of levels out and then goes back up. So here again, from 2 to 3, and 3 to infinity. Okay. if we look, we can do the same thing with the decreasing. So here we can say f is decreasing. On the intervals where the slope is negative. Okay? So here I'm thinking when the slope is coming downward, that's the places my derivative is negative. And so here I can see coming in from negative infinity up to negative 2. From negative 2 to negative 1 and negative 1 to 0, we already know it's increasing. And then over here from 2 on down, I can see from 0 to 2, it is decreasing. And then after that, it's increasing again. Okay. So, for critical points, and I'm going to start with the values. Let's start with just the x values, the critical values of our function. So all the x's that are somewhat different, meaning I can't tell whether the slope is positive or negative. There's something else happening there. Well, it just so happens it coincides with all the places my intervals start and stop. And we can see that in the graph. So at x equal negative 2, we can see it's changing from negative to positive. At negative 1, we see there's, even though it's positive and positive, there's a break in the graph. At x equals 0, we can see it's going from positive to negative. At x equal 2, we can see it changes from negative to positive. And x equals 3, that was the point where it kind of levels out before it keeps increasing. Okay. So our critical points, if we start looking at relative maxes and mins, we can only use the values where the function's derivative is defined, meaning where f prime of x is equal to 0. So places like negative 1, we know are not going to be relative mins or relative maxes because the derivative is undefined there. Okay? So for relative maxes, we're looking for places where it's a critical value and the slope changes from positive to negative. Okay? So we can see here, for example, it goes from positive to negative at x equals 0, and x equals 0 is a critical point. So we have a relative max at 0, where the y value is 2. Okay? Notice these are ordered pairs. Okay? For relative min, we can do the same thing. So here again, we're looking for places where it's a critical point, but it changes from decreasing to increasing. And so here we can see at x equal negative 2, it goes from decreasing to increasing. So at negative 2, y value there is 1. That ordered pair is going to be a relative min. Likewise, if we look on the positive side over here, at x equals 2, we can also see it goes from negative to positive. And here the y value is negative 3. Okay. So it is possible for a function to have more than one extreme value and more than one of each type extreme value. And there can be places that are critical values, but not extrema. So for example, negative 1 is a critical value, but it's not an extreme value. And likewise, 3 is a critical value, but it's not an extreme value. So to find extreme values, we're going to use the derivative to find the critical values and then use those to determine where the function is increasing and decreasing, and then get our extrema. Okay. So first we'll take the derivative of the function, set the derivative equal to 0, or find out where it's undefined. Those values will give us those extreme or critical values we were talking about. Then we're going to take a number line and use the number line to plot the critical values. Once we have them on a number line, we're going to pick test points in each region so that we can determine the sign of f prime of x. And so here, when we're testing these points, we're going to plug them back into the derivative to see whether or not f prime is positive or negative. Last, once we have those values, we can determine where the extrema occur and find the ordered pairs. Okay. The last part, I have a star by this because in some cases you're going to be asked to graph the function. And once I have this information, I should be able to get a pretty decent sketch of the graph. Okay? At least for the ones in this section. There are going to be ones later where you're going to need a lot more information. Okay? If I'm looking at steps 1 through 5, this is what we call the first derivative test. And as I said, we're going to do more later on, so we'll talk about other tests that we'll have. But for now, the first derivative test is the one in which I use the first derivative to figure out or test where my extrema are. So let's take a look at this example. F of x equals 2x squared minus x to the fourth. In this case, we want to find the critical values and essentially find the extrema, and if we can, sketch the graph. Okay. So in this example, first thing I'm going to do is find my derivative. So using my power properties, we can see 4x minus 4x cubed is going to be my derivative. From there, I want to find my critical values. So I want to set f prime of x equal to 0 and find out where the function is undefined. Okay. In this case, 4x minus 4x cubed equaling 0. We can see to solve this, I'm going to factor. So 4x will give me a 1 minus x squared. And I can take that down a little bit further. And now that I have some factors equaling 0, I can see that x had to be 0, 1, or negative 1. Okay. For the other side, f prime equaling undefined, or where is f prime undefined? Well, in this case, f prime is polynomial, so we know the domain is all real numbers. So in this case, this is never going to be undefined. So now, my critical values, I want to take and I want to put them on a number line. And for each region, I'm going to pick a test point between those critical values. So over here I can pick something like -2, -1/2, 1/2, and 2. And again, I want to plug these into the derivative to test whether or not the function is positive or negative. Now here, when I'm plugging back in, you can either plug it back in here at f prime when we first took the derivative, or you can use this factored form. The nice thing about the factored form is I don't actually need the value. So if I'm using the factored form, I can just plug in to see whether or not each factor is positive or negative, and then use that to determine whether f prime is positive or negative. So here, if I look at -2, for example, I can plug in here. I'm going to see if that's going to come out negative. Plugging -2 in there will be positive and negative. So a negative times a positive times a negative, that's going to give me something positive. Okay. Same thing with -1/2. Here again, that's going to give me something negative. That'll be positive. -1/2 in there will be positive. So overall, I'll have something negative. At positive 1/2, this will be positive, positive, and positive. And at 2, the only thing that's going to change, well, that'll be positive, that one will be negative, and that one will be positive. Okay. Now, what's useful about these is this is telling me the function is increasing, and here it's decreasing. So here I'm going to have a relative max. Likewise, in this interval it's decreasing, and then it changes to increasing. So here I'm going to have a relative min. And lastly, positive to negative says it's increasing, then decreasing, so that's going to be a max. So, looking at our information, this says that f is increasing on the intervals from negative infinity to negative 1, and again from 0 to 1. F is going to be decreasing on the interval from negative 1 to 0 and from 1 at 1. So for our extrema, we have a relative max at the point negative 1. Well, to get the y value, we've got to plug back into the original function. So when we plug negative 1 in here, we get 2 times 1 minus 1. And we also had another relative max over here at positive 1. Same thing, if I plug back into the original, you can see I get a value of 1. For the relative min, we had 1 at 0. Plugging back into the original, we can see that the y value is 0. Okay. So there's our slope and our extreme values. Now we can use this information to get a picture. Okay. So here, plugging in this information, I'm going to start with the extrema. So we have a relative min at 0, 0, relative max at 1, 1, and negative 1, 1. Here we can see it's increasing from negative infinity to negative 1. So I'm going to have to come up from here up to my max. And again, you can see there are some other intercepts in there. Okay, you can actually find those intercepts. There's definitely going to be one between negative 1 and negative 2. From negative 1, I'm then going to decrease to 0, increase to 1, and decrease to infinity. And so there would be a sketch of our graph. And notice here, unless I ask for the intercepts, I don't actually have to go back and find them if it's just a sketch. If it asked for the intercepts with this, then you need to make sure you go back and actually list what those are. Okay. In our next example, let's do the same thing. So we want to use the increasing or decreasing, so the slope, and the extrema to get a sketch of the graph of the function. So here f of x looks like x squared e to the x. Okay, so again, the first thing we're going to do is find the derivative. So here f prime of x looks like, here we're going to need a product rule. So 2x e to the x, derivative of the first times the second, plus the first times the derivative of the second. Okay. Again, once we have the derivative, we want to find the critical values. So we're going to set them equal to 0 and set it equal to being undefined. In order to do that, I would say to clean this up first. So here we can pull an x out front We can pull an e to the x out front, and what's left is a 2 plus x. This just gives us a nice factored form for trying to solve the equations. Okay. So now we'll look at when f prime is 0 and when f prime is undefined. Okay. It's going to be 0 when x e to the x times 2 plus x is 0. Again, this factored form is nice because now I can just set each factor equal to 0 and solve. Okay, so obviously x will equal 0. E to the x is never 0. Remember, e to the x is always positive, so we can exclude that one. And then 2 plus x equals 0 when x is negative 2. Coming over here to when it's undefined, we can see each of our factors is either polynomial or it's an exponential. In both cases, the domain is all real numbers, so this is never going to be undefined. So, using this information, we are going to look at the number line. We're going to plot the critical values and determine the sign in between them. Here, since we only have 2 critical values, we just have 3 places we need to test. So we can look at a negative 3, a negative 1, and 1. Okay. Again, we're going to plug this into the derivative. Factored form again is very nice. So plugging 1 in there, we can see we get positive, positive, and positive. If we use negative 1, we'll get a negative. E is still going to be positive, and that's positive. And putting in negative 3, we get negative and a negative. E again is still positive. Okay. So looking at this information, we see that it's going to be increasing and then decreasing. So we have a max there. And then over here, we have it's decreasing and then increasing. So we have a min. So f is increasing on the interval from negative infinity to negative 2 and from 0 on. F is going to be decreasing on the interval between negative 2 and 0. Okay. For our relative max, we can see that occurred at negative 2. Here, to get the y value for that point, we need to go back to the original. So we can see if we plug in, we're going to get a 4e to the negative 2. And then for our relative min, same thing. We can see it occurs at 0. And when we plug back into our f equation, we see we get the point 0. So with this information, again, we can get a sketch of the graph. Sketch, again, not exact. Again, we can go back and find intercepts if we need to, or get more information. But this will give us an accurate picture of what the graph looks like. Okay. So first, again, we're going to start with the extreme values. So we have a relative min at 0, 0. And here, at negative 2, we've got a relative max of 4e to the negative 2. Okay. E to the negative 2, that's a 1 over e squared, which is a really small number, multiplied by 4. So it's going to be up in here somewhere. Looking at our increasing and decreasing, we see it starts increasing from negative infinity to negative 2. Okay, so it's going to come up to our max point. Then we're going to decrease down to 0. And then we increase up to infinity. And then it just keeps on increasing. Now here, I stopped and started my graph short because we have to consider what happens over here. If we look at our intercepts, we can see that the only intercept is at 0, 0. So I can't have my graph come this way even though it's increasing. But in this case, what we'll notice is that e to the x has that asymptote, and we actually get that same asymptotic behavior for this picture. Okay. So there would be a sketch of our graph for f of x equals x squared e to the x. Let's take a look at one more function. So let's look at f of x equaling 2x squared over 4x squared minus 25. Okay. We want to do the same thing. We want to look at where it's increasing and decreasing and find the extreme values so that we can get the graph. Okay. So again, we'll start with the derivative. In this case, we're looking at a quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom, all over bottom squared. Okay. So here, again, we want to simplify where we can. We'll notice 4x squared and 4x squared gives us a 16x squared minus the 2 times 8. Sorry, 16x cubed minus the 16x cubed from the other side. Those will cancel out, and so we're just looking at negative 100x over 4x squared minus 25 squared. That's our derivative. Okay. For our critical values, we want to set that equal to 0 and find out where it's undefined. Now, the nice thing about rational functions is when I'm trying to find these two things, I only have to consider part of the function. So in the case of f prime being 0, well, that's only going to happen when the numerator is 0. Okay? So here, I just need to know when 100x is going to equal 0. Well, in this case, that's just at x equals 0. For the function to be undefined, because it's rational, I know that's going to happen when the denominator is equal to 0. So here, we just need to determine when this equation is true. So we can square root both sides. We see we still get 0. So 4x squared has to equal 25. X squared will equal 25 over 4. And solving for the root, we'll get a plus or minus 5 halves. Okay. So here we've got 3 critical values. We're going to go ahead and put that on the number line. So using the number line, we've got negative 5 halves, 0, and positive 5 halves. Okay. Now we need to test some points in each region. So for this, we can test 3, 1, negative 1, and negative 3. Okay. So looking at these values, we're going to plug it back into the derivative. Another nice thing about this particular function is if you notice in your derivative, the denominator is squared. So it doesn't matter what value I put in here, this is always going to come out to be a positive value. So here, when I'm testing these points, I just need to consider what happens to the numerator. So if I plug in 3, I can see that's going to be negative. At 1, also negative. Negative 1 gives us something positive, and negative 3 is positive. So here, we see it goes positive and positive, meaning increasing and increasing. So no extrema there. There's no sign change. Here, it goes from positive to negative, so we have a relative max. And here, we're negative and negative. So again, no extrema. Okay. So now we're going to list this information and then get our graph. So f is increasing on the interval from negative infinity to negative 5 halves, and again from negative 5 halves to 0. Now notice here I didn't just put negative infinity to 0, even though both of those are positive. Here, because negative 5 halves is undefined, I know it can't be increasing there. Okay? Same thing for the decreasing. So here f is going to be decreasing on the interval from 0 to 5 halves and from 5 halves to infinity. Okay. As far as our extrema go, we have a relative max. Here we saw that's occurring at x equals 0. For the y value, again, we can plug in, and we'll see that we'll get another 0. And then for relative min, well, here we noticed there were no other extrema, so this is just none. Okay. Now let's get the graph of this picture, of this function. Okay. As we go to graph this, a couple things to keep in mind. So as I've said, one of the things you're going to want to make sure you do is use your extreme values, but also if there's any nice intercepts. And in this case, it's very easy to see 0, 0 is the only intercept for this function. But the other thing to notice is because I have a rational function, there are places where the denominator doesn't make sense, where it's undefined. And if you notice, it just so happens those values are where the function, the derivative, is undefined. In terms of the graph, those show up as vertical asymptotes, right? Any place the function is undefined is either going to be an asymptote or just something not in the domain. Okay? So here, we'll go ahead and plot those, and let's go ahead and plot our extreme value, which is at 0, 0. Okay? So, starting over here at negative infinity, you see from negative infinity to negative 5 halves, it's increasing. Well, here there's kind of two options. So increasing could mean I'm increasing this way. So starting down here and going up towards the asymptote. The problem with that is I'd have to cross the x-axis. And as we've said, we only have the one intercept. So here I know I can't be below and then come up to the top, which means it's got to increase from this direction. From there, negative 5 halves to 0 is still increasing. This one I need to hit my maximum. So I know it's got to increase to that point, which means I'm going to get something that looks like this. On the other side of 0, I'm now decreasing. So from there, I'm going to decrease again to the asymptote. And then from 5 halves to infinity, I'm decreasing again. And again, for the same principle as before, I know my decreasing can't go to negative infinity, otherwise I have to cross the axis, and I don't have any more intercepts, which means it's going to decrease and then go towards 0. So here's my graph for f of x equaling 2x squared over 4x squared minus 25.